Kia ora all. I am about to go through the TGC Level 3 Derived Grade Chemistry exam for 2024, and this video will just go through question 1. So our first question is about optical isomers, and you can expect a question about optical isomers. So our first thing we can do is find the chiral carbon of malic acid, which is found here. And let's center our chiral carbon in both of our diagrams. Let's draw a 3D tetrahedral arrangement. All right, so just mirror images here. And then the 4 groups, 1, 2, 3, and 4, just need to get arranged around that central atom. Just make sure that you join the right atoms. That means not joining, for example, joining like this. Okay, so recognizing which atoms are joined to where. It doesn't matter which you put in which order, so I'll just put the OH here and the OH there, and I will put the H there and the H there, and then the CH2COOH. I actually find that easiest to do extended. And then CH2COOH. All right, so that was a little merit question. And then the next one is explain why malic acid is able to form enantiomers and how samples can be distinguished. So number 1, enantiomers or optical isomers form when there is a chiral carbon. And we need to explain what that is. A chiral carbon is a C atom with 4 different atoms or atom groups, not functional groups, and some of you did that wrong, sorry, bonded to it. And always get used to, in this case, HOH, COOH, whoops, and CH2COOH. The enantiomers can or are probably non-superimposable or superposable. I know there's a little argument about that. Mirror images. To distinguish, now you just need to get your language right here. So some of you nearly got your language right, but not quite. To distinguish the 2 isomers, shine plain polarized light through a sample of the enantiomer. One enantiomer will rotate, it's an important word, rotate the plain polarized light to the right, or clockwise is fine. The other to the left at an equal angle. And that's the only way we can distinguish them. So that one just needed quite precise language, and you will get a question like that in your NCA exam. Next question is a polymer question with a polymer with a big name, and it doesn't really matter what that name is. A homopolymer, and I often talk to you about that being one monomer which is repeatedly joined, so an AAAA polymer. And the first question asks you to figure out what the monomer was. So basically it's copying. We copy this entire skeleton here, and then we just need to reform the functional groups. So because we're making a polymer, we're only making polyesters or polyamides, and obviously there's no N, so this is a polyester. So it must have come from either a carboxylic acid or an acyl chloride. I'm going to choose an acyl chloride and an alcohol. If you choose the acyl chloride, the small molecule removed will be an HCl, and it will be water if you chose the carboxylic acid. So it says explain the type of reaction occurring. So we need to explain condensation, and we need to explain polymerization. So that has to be in our answer, and why the monomer needs two different functional groups in order for the reaction to occur. So condensation reactions involve the joining of two compounds with the removal of a small molecule. In this case, HCl. So see how I'm always doing in this case. So I'm linking it back to the question. In this case, HCl. This is done repeatedly with many monomers, so that a very large chain, or a very long chain, polymer is formed. To do this, we need two different functional groups, and here we need one alcohol and either a acyl chloride or carboxylic acid, so that an ester link is made at each end of the molecule. Probably each end of each molecule. So I guess a couple of the points you could also make if they had two of the same functional groups, there would be no ester formation. So there'd be no ester link. And if there was only one functional group on each molecule, we could make one link but not a polymer chain. One link but not a continuous chain. So I didn't really expect those last points, but I just wanted to point out some of the things you could have made continuous chain. Okay, so that's B. Over here to B2. So this one is a biodegradable polymer. It can be broken down by microbes. It's a bit irrelevant. And in aqueous conditions, obviously that's important because it's bolded. Discuss the reaction that occurs in the breakdown of the PHV polymer, include conditions and similarities and difference when different conditions are used. Okay, so let's start with the reaction because that's always the way to start with it. So our polymer looks like this. So we're going to break it back down to the monomers, except we need to decide what our monomers will look like in, obviously, acid and base hydrolysis. It's kind of hard for me to remember what it is. Sorry, I just need to put back. So I've got 3 carbons here. And it's slightly painful, isn't it? A double bond to O and CH2, CH3. Okay, so that's the basic carbon chain there. So we've got acid hydrolysis. Oh, crikey, I've just noticed I'm far away. And we've got base hydrolysis. So the products for acid hydrolysis are essentially the same. A lot of copying here. Right, there will be an alcohol group reformed because alcohol groups are neutral. However, the acid group needs to have its proton attached because that's what happens in acid hydrolysis. I can put in here H2OH+, and I need to put heat because hydrolysis does need heat or reflux. The basic hydrolysis is very similar. The alcohol group stays, but the base group is an O-, and you could put an Na+ or a K+ in there. So once I've done my equation, I just need to put that into words. So I need to say this is a hydrolysis reaction where water is added, and that essentially breaks the ester links to reform small monomers. And the similarities, so both need H2O and heat. Acid hydrolysis requires an acid catalyst. And all functional groups able to be protonated are protonated. Whereas base hydrolysis requires a basic catalyst, and all possibly deprotonated functional groups are deprotonated. And you can refer to your results up here a little bit more specifically than I have here. So hopefully you will get a question on acid and base hydrolysis, so it's really good to go through this one. And quite simple, like you really just have to get down to the understanding and the rest is copying. Last part of question 1 is a big reaction scheme. So looking at our carbon chain here, we've got 4 carbons. You need to make sure that you keep your 4 carbons. And our first reagent 1, that's actually quite hard to figure out. So we're going to need to go down to here to start. 1, 2, still got 4 carbons. And we're going to start with NaBH4, which is a reductant, but it only reduces ketones, not carboxylic acids. So the carboxylic acid will remain and the ketone gets reduced to an alcohol. So I just look at the functional group chemistry first, and then I'm going to put all my hydrogens on. Some of you still like to do condensed formula, and that has resulted in a few errors. So I do still continue to think extended structural formula is the most useful. Let's go down to the bottom now. So we've still got 1, 2, 3, 4 in our main chain here. So this is our main chain. And we've obviously added this on. So we've obviously gone here from an acyl chloride plus an amine. So the amine must be our reagent here. So, and that needs it to be in alcohol. And that, therefore, must have been that ketone group, just copying it all down, and then C double bond to O, Cl. Therefore, I look at what's the difference between this one, and it's only the Cl. So I've added PCl3 or PCl5 or SOCl2. Going back up here, I need to go from a double bond to, so I need some oxidation in here. So you can see I've got an OH group here and I've got a ketone. So there must be some oxidation in here. This implies a major and minor. So it looks like this is going to be addition. And because I want to oxidize something to make a carboxylic acid, I'm going to go ahead and say I need an OH in here. So I'm going to add H2OH+. And in this one here, I'm going to keep that OH that's already there. And I'm going to add an H and an OH across that double bond. And of course, it's major and minor depending on which way round I add the H and the OH. I don't even really need to talk about major and minor here. I'm not asked to. The only important thing is that the OH in this one here must be on the end carbon because it turns into a carboxylic acid. So I'm going to put that OH there. Fill up my H's, and then this one must be the other way around, so it must have the OH on the second carbon, and then I would put in my H's there. I'm not going to put them in now, but you can see where they would go. The only thing that's left is how do I get from this alcohol to this carboxylic acid? Well, I can pick either MnO4- and H+ and heat, or Cr2O72- and H+ and heat. That one's really picky. You can get an M without getting all of the conditions right, but to get the excellence, it needed to be pretty perfect. And that's the end of question 1.